In this lesson, I'm going to go over the particle update section. It's going to be a long video, so I decided to break it down into 2 lessons. In the first lesson, I'm going to talk about how we can control the behavior and movement of the particles using forces. I'm going to explain how each one of these forces will work and affect the behavior of the particles. I'm going to spend some time in that area. And the next lesson, I'm going to talk about how we can control the shape and the look of the particles over their life, including, for example, size and color and anything else that relates to their look. All right, so let's get into Unreal. This is where we left off from the previous lesson. So we already generated particles and it's time to control their behavior and their shape over this lifetime. So I'm going to delete the solve forces and velocity because I want to just prove a point here. I'm going to delete this. I'm going to add some forces here and let's see where we can find those forces. So just like before, any module that you want to add, you will click on this plus sign, and I am going to go directly to the forces. Gravity force is one of the forces that most of the time we use. I'm going to add the gravity. And let's pause here and see what's happening. Even though I've added the gravity force here, it's not affecting the particles. And also, if you notice, there are some warnings showing up here. So what this warning is saying that I've added some forces here, but in order for Niagara to be able to calculate the simulation, it needs to have another module that comes after any force that we add here, so it can solve this simulation for us. So that's the first thing that this warning is saying. And soon I'm going to show you where else this warning will show up. So I'm going to just hit fix issue and it will automatically create the solve forces and velocity for me. And now you can see this gravity force is affecting the particles, right? Keep in mind that if I start adding more forces here, I no longer need to add another solver because this solver will take care of all of the forces together. So let's see what this gravity force does. Of course, I mean, it's a gravity, so it has direction, and also whatever value you type in here will act as the force itself, as the strength of the force itself too. So currently it's in the direction of negative z, and its strength is 980. So if I'm happy with the direction, but I feel like the gravity feels a little bit too strong, I can reduce this value to something lower than that, for example, 100. So it's going down by the same gravity in the same direction. However, this time the strength of the gravity is a little bit lower. And that's why the particles, since they already had that initial direction using this wind force in the spawn, they have that direction going up. And then they're being affected by the gravity after that, and they're falling down. So let's also spend a little bit more time here to understand what we have done. So in the particle spawn, at the moment of creation, we have a wind force that its direction is upward with a scale of 150, as you can see. And it only affects them when they are being born, and it will let them go after that. After they're born, the particle update comes in play, and it affects the particles while they are alive. And in this case, we are only having the gravity force, so they go up and then they fall down. It's worth mentioning that, again, this wind force is only affecting them right in the first frame and nothing more than that. Just to prove that, I'm going to add a new wind force here. So forces, I'm going to bring in the wind. This is another place that this warning will show up. The only thing that this warning is saying that your forces are supposed to be before the solver. So either I can manually bring it down, or I could just simply click on that fix issue and it will bring it down for me too. So let's just undo it, and I'm going to just click on this fix issue and it will do the same thing. Temporarily, I'm going to remove this gravity force and I'm going to make these 2 wind forces to be identical. I could even duplicate that wind force to make sure that they are identical. I'm going to Control C, come here, Control V to copy and paste the same force down here, and I'm going to fix the issue so it's before the solver. And now let's see what's the difference between having a wind in the particle spawn and having a wind in the particle update. Let's turn this off. The particles are having that initial force, initial velocity because of this wind force. If I turn this off and turn the other one on, you're going to see the difference. See, the particles, when they're born, they do not have an initial velocity. They are being affected by the wind after they are born. They are standing there, and eventually by this wind force, they are gaining some speed. And you can see that if I zoom out, they gain more speed as they go. as opposed to, again, if I go back to the other version, having the wind to be in the initial stage or in the particle spawn stage. They are having that force affecting them right at the moment they are born, and that wind is no longer in effect, and that's why these particles are not accelerating, they are not gaining more energy, they are not speeding up. They gain that initial speed and they travel with the same exact speed as they travel upward. I really like the result of having the wind in the particle update. I'm going to delete the one in the particle spawn, and I'm going to enable this one. Okay, I like this one. Okay, the next force that I'm going to talk about is velocity. I'm going to add velocity. And velocity is technically adding some speed to the particles to push them. So I'm going to use add velocity. And of course, we're going to get the same warning. And I'm going to hit fix now and see what happens. I added that velocity to the particle update. Let's fix it. You'll see that it will bring this add velocity force all the way up to the particle spawn. This is indicating that some of these forces, even if you try to add them to the particle update, they're only affecting the particles at the moment of creation. So they're supposed to be in the particle spawn section. Just to show you what's this add velocity doing, I'm going to turn off the wind velocity. And let's just focus on the add velocity. And I'm going to increase the value in the z direction to 50, for example. And you can see that it's now affecting the particles going upward. And you can see it's almost similar to where we added a wind force here in the particle spawn. And you are now getting that most of them, if they belong to the particle spawn, they are only affecting the particles right in the first frame. So this add velocity is only adding an initial force or velocity for these particles, and it will let them go. Or for example, if I start adding velocity in cone and then disable this add velocity just so we can focus on the add velocity in cone and see what it does. I'm going to give it some strength, 100. You can see now I'm having almost the same result in z direction, with a small difference that this add velocity in cone is having a cone shape to act as the force, and you can see it's also distributing these particles. It's scattering these particles along that cone axis, which is z positive value, and that results in a different behavior if we only have a velocity or we have a velocity in cone. Just for the sake of seeing some more interesting results, I'm going to turn on gravity here, and I'm going to increase the strength of my velocity in cone. I'm going to change the size of the sphere location to something lower, so we are having a smaller radius for the emitter. It's an interesting result. Cone angle 45, let's increase that to 80. Very nice. The next force that I want to talk about is vortex. We have vortex velocity and vortex force. Force belongs to the particle update, velocity belongs to the particle spawn. So vortex force, fix the issue. And I'm going to turn off the gravity for a moment. I want to see what that vortex force does. Let's bring down the strength of the velocity in cone. If you notice here, the particles are sort of swirling around this z-axis now, right? That's only because we added this vortex force, and that vortex force is creating a vortex field for us. So it's swirling these particles along that axis. If I turn that off, it's only velocity in cone. They're all going up, and then bringing in the vortex force, it tries to twist them along that axis. So let's see what we have in the vortex force. Of course, since it's a force, we have a strength. So if we wanted to go even faster, I'm going to increase the force strength. This defines the axis that these particles are supposed to twist around. So if I want them to twist around the x-axis, I can change this to 1 and change z to 0. And now these particles are twisting around the x-axis. I'm going to change it back to z-axis. This is a vector direction, so it's pointing in the x direction and in the z direction, which makes it more diagonal. So let's set it back to 1, to 0, and the vortex to something lower than that. And there is another attribute here called origin pull amount, which help us to control these particles so they don't go crazy and start getting far from the source. So if I increase this pull amount to something higher, and this value is a little bit sensitive, so let's just start with some small values. I'm going to type in 1. You can see that the particles are still being affected by the vortex, but they are not going that crazy anymore. Let's just, for comparison purposes, increase that to 5. Now you can see that all of these particles are being pulled in to the origin, and this is coming from this origin pull amount. Use influence fall off helps us to gradually get rid of this pull amount. So meaning that the particles that are close to the center, they are going to be pulled stronger. And if they somehow manage to escape that fall off field, they start gaining some energy and they will not be pulled in by that pull amount. So let's first decrease the value of the pull amount to 3. So we will let some of these particles to be able to escape. And I'm going to enable the use influence fall off. And right now the fall off radius is set to 100, meaning that after a radius of 100, those particles are not going to be affected by that pull amount anymore. So that pull amount is going to be only effective within this region of radius of 100. How fast this force is going to dissolve, that depends on the fall off exponent. If I change it to 2, it's going to lose its energy faster and faster. If I set it to 3, it's going to lose it even faster. Okay, let's set it back to 1, the radius to 100, and let's keep it here. And I'm going to decrease the value of pull amount to even something lower than that. So we will let some more particles to actually escape from that field. The other force that I want to talk about is drag. This drag force is your friend. Use it a lot and a lot. It will allow you to hold these particles even if they're affected by some very strong forces. So this drag allows you to drag them so it will hold them and it will make them more controllable. You can see now, because of that drag, these particles are not escaping that much. They are losing their energy as they grow older. And this drag value is also very sensitive. So if you wanted to affect the particles even more, you can change this to 2. And you can see that these particles are being dragged behind. And usually when you start introducing drag, it requires you to go back and modify some of your forces. For example, I need to still push the particles apart, but yet being affected by this very strong drag. So let's increase this force to something higher. Now they can travel more because the force is pushing them, but because of the drag, you can see that they're immediately losing their energy. I'm going to make it even look more explosive. So I'm going to increase this velocity to something very high and then increase the drag. So they explode, but they suddenly lose their energy. This is because of the high value on the drag, and these speeds are because of the high value on the velocity. Okay, so that is it for drag. Let's introduce a couple more minor forces, the ones that might help you. The point attraction, and the name suggests what it does. Let's see, I'm going to turn off the drag. I'm going to turn down the velocity to something more manageable. I'm going to turn off the vortex force as well. So point attraction has a strength and it has a position and a radius. So point attraction by default is sitting in the position of my emitter because they're both in the origin. If I like it, I can keep it there. If I don't like it, I can actually change the position using this attractor position offset. Let's use that one. So let's have the position attraction point to be somewhere along x-axis. And I'm going to increase the strength to something high so I can see the effect of it. See how they are being attracted to that point in the word space. Let's change this value to 60. Even farther from the origin. Now it's too far and its strength is not enough, so they actually don't get into that trap anymore. So let's make it 80. The particles that are closer to that point, they will be attracted to it. The ones that are a little bit farther, they won't. Fall off exponent is similar to the vortex that we had. This is how fast they lose their energy. And the radius of the attraction, of course, we know what it means. And right now the point is right here, and within the radius of 100, it's attracting the particles. So if it's too much, I'm going to increase that to 50. And now it seems that it's very small and there is no particle that gets into that radius. So 70. And you can see how easily I can art direct that. For example, I can have 2 of them. I can duplicate this, Control C, Control V, and the other one I'm going to push it in the other direction, so -80. And now each one of these 2-point attractions are actually attracting those edge particles towards themselves. And by the way, you can rename each one of these modules by right-clicking on it and choosing rename, or the shortcut is F2. I'm going to rename this 1-point attraction. I'm going to increase their strength to something higher, so they pull the particles down. Now that we are here, let's also see how this fall off exponent affects that result. So I'm going to increase that to 1. You can see that it's helping this point attraction to attract the particles even more. So if I change it to 0.1, it's not affecting them that much anymore. So 0.3. And it's a combination of changing each one of these individually. So if I set it to 0.2 to make it go faster or slower, I can see what happens if I increase the strength of it. What if I duplicate it one more time and name this one back? And I'm going to push this in the Y direction. That's cool. Now that we learned about this point attraction, I'm going to delete them or disable them, and I'm going to talk about another type of attraction, which is line attraction force. Of course, it's acting similar to the point attraction, but this time we are having 2 points in the space that defines a line for these. So let's make this line to go vertically in the Z direction. I'm going to change these values to Z direction. So it's saying that there is a line that starts from 0, 0, 100 and goes all the way down to 0, 0, -100. Let's increase the value of the strength to something higher. Here we go. That line is now attracting these particles. And you can see this is 100 and -100 is down there. Let's turn off velocity and cone, and I'm going to change the sphere location radius. Let's first start with only having the radius to something very high, 500. This is the emitter, and I'm going to turn on line attraction force, and now they are being attracted inside. Very nice. Let's go back to our original value of, I think, 10 for the emitter source, and I'm going to turn off the line attraction force, and I'm going to turn on velocity and cone, so we're back to our original simulation. And the last force that I want to talk about is the curl noise. Curl noise is a type of force that has some forces based off of a noise texture that is random, and depending on the properties of that noise, your force field will behave differently. So let's first just see what we have there. Curl noise. I want to make it a little bit more obvious for you, so I'm going to turn off velocity and cone, and I'm going to only add a velocity, a simple velocity that pushes the particles upward, so we can see what the curl noise does. And as soon as we enable the curl noise force, it will push them in a random direction. I could even turn off the velocity itself, so the particles are only being generated on the sphere, and then introduce the curl noise force. They are only being affected by the curl noise now. And you can see how beautifully it will push the particles apart, and it will make them to look more natural. But what these two attributes mean? Okay, so I've created this simulation that is representing the force field for us. So these are not particles, they're only representing the force field. Let's assume that each one of these lines are actually pushing each one of the particles into space. On the corners, you're seeing that I'm having these noisy textures. These are defining how this curl noise is generating these force fields that affects our particles. So if you remember, we had 2 attributes here, noise strength and noise frequency, and I'm trying to show you what each one of these 2 do. The most important one is the noise frequency. So let's go back to our simulation. So in this case, we are seeing the same curl noise with different frequencies. So the first one is having a high frequency of 50. The next one is having a lower frequency, 30, 20, 10, 5, and 2. And you will see on the corners what this frequency mean. So in the higher frequency noise, you'll see the noise is very, very small. And it means that when it's making a force field to affect the particles, even if two particles are very close to each other, since the noise is different for those 2 points in the space, these are actually being pushed in different directions. As opposed to the low frequency noise here, if 2 particles are close to each other, the force that is affecting them is almost similar. So you can see how differently each one of these frequencies are resulting in different behaviors in the particles. This is in the perspective view, just to make it a little bit more understandable. I do have some other views here as well, so let's switch to the front view. So high frequency, everything's randomly in different directions in high frequency noise. In lower frequency noise, things are having a more subtle change over the field. So you can see in another direction, top view. So high frequency, lower frequency, and you can see how different the result is. But we also had another attribute here, right? We have a strength. This strength is referring to the amplitude of our noise, how dark or bright our noise is. It's only saying that with the same random direction being defined by the frequency, how much it's supposed to push them. And that's why it's called a strength. So if I go back to that simulation, this time we are only comparing the amplitudes. The frequency for all of these 3 simulations are the same. The only thing here that is changing is their amplitude, their strength. So on the left, you can see that the field is not that strong. The curl is not that strong. In the middle one, it's getting some strength. And on the last one, the amplitude or the strength is set to 4. And you can see, although each one of these directions for the forces are the same, they are identical, because they are having the same frequency, but it's only the strength of it that is changing. So let's go back to Unreal now that we learned about the difference between these two, and see the results here. This is a very strong kernel noise. I'm going to reduce it to 150, and you can see now the frequency is set to 50. If I want them to have a more subtle movement altogether, I need to bring down this frequency to something like 2 or 3. Now you can see they're moving forward almost all together because the scale of that noise is much larger, or the frequency is very low, which makes the force field to be almost identical in the points that are close to each other. So let's make it 5. Here we go. 10. More randomness. The trick here is when you are dealing with kernel noises, you do want to have some high frequency and some low frequency noises to affect your particles. So it's a matter of adding another kernel noise with different values. So in this one, I want to have it to be very high frequency, or even 60, to jitter them around in their position. So I'm going to rename this one high frequency, and this one low frequency. For the high frequency, let's have them to only affect them by a strength of 60. I can even push it further, so again we can see the result. There we go. So depending on what you are trying to achieve, you want to play with these amplitudes individually. Now that we have all of these forces, let's start introducing all of them. So I'm going to have some gravity. It seems that the gravity is too high, so I'm going to reduce it to -200, even lower than that. Let's introduce some wind force going upward. It's too much again. Let's give it some drag. Lovely. But again, depending on what you're trying to achieve. Point attraction and line attraction, I don't need them. I'm going to delete them. Vortex force, let's enable that. It's too much. Okay. Well, I'm going to turn it off for now. All right, so this wraps the first section of dealing with the particle update. In the next lesson, we are going to see how we can control the shape and the color and the size of these particles over their life.